radiative efficiency. So it's a very good, it gives you a very strong photospheric component. So that's one way in which you can get these relative proton-neutron collisions is, just the radial motion. The protons and the neutrons are moving radially, but then they start drifting relative to each other. The neutrons are slower, the protons are faster, they collide, and you get dissipation. Alternatively, you can have the jet has a structure. Let's say there is a faster, larger Lorentz factor, Borg Lorentz factor here, the slower Borg Lorentz factor on the outside of the jet. So here you have fast neutrons and protons, and here you have slow neutrons and protons. But the neutrons, being uncharged, they can drift across magnetic field lines, and they can walk into the fast flow, and then they will have a very different Lorentz factor than the fast-moving neutrons and protons, and again you get inelastic nuclear collisions. So the result is that you have the thermal, if you look at the population of electrons, you have thermal electrons initially, and then you produce these non-thermal electrons because of the of pi naught, the pi plus decay. And the pi plus decay produces these relativistic positrons which interact with the thermal protons, and they reheat them. So the thermal protons, you get these reheating. And you get two populations, reheated thermal electrons and non-thermal electrons. And if you calculate what is the escaping spectrum from the photosphere, these are Monte Carlo calculation, you get these nice spectrum which has a pretty decent low energy slope and a pretty decent high energy slope. These where you transition from the thermal electrons to the non-thermal electrons, and you get up to the GeV range, and you can get something that looks like that single broken parallel extending to the GeV range. 2010. What about the extra spectral component that looks like that Fermi sees? Well, this was a calculation where magnetic field effects were completely ignored for simplicity. But if you include magnetic field effects, then you get synchrotron radiation, and the synchrotron radiation gets upscattered, and so you get something that starts looking like you have here a second component. You have something which is steeper, but then you have a little shoulder. So it's not yet a full-fledged second component, but it's going in that direction. So these are follow-up calculation by Boole. The other way of dealing with the internal shock problems is to consider modifications of the standard internal shock model paradigm. So these modifications are intended to mitigate or even solve the internal shock problems. And there are two types. One of them is to consider that there is magnetic dissipation in the internal shocks. Magnetic dissipation is very efficient, and it will accelerate both electrons and protons. The problem is that it's difficult to calculate quantitatively. When you do MHD, you have free parameters, and you can adjust them, and it's rather messy. And doing numerical simulations, particle in cell, it's very expensive, and always you have to put in various assumptions. So you can do approximate calculations, but they're not terribly predictive. That's the problem. You can get things that look reasonable, but not something that you would sort of be very confident of. Another approach is to consider hadronic effects in the internal shocks, meaning that whereas in the simple leptonic approach you ignore what the protons are doing, they just provide inertia. In the hadronic approach you say that if you have shocks, you will accelerate protons as well as electrons. They will be first-order Fermi accelerated, and it will produce relativistic secondaries, and the relativistic secondaries can be reaccelerated by second-order Fermi acceleration, and that will produce slow heating. And slow heating is the one thing that can solve the efficiency problem and the spectral problems of internal shocks. So Mouras et al. Have done a more detailed calculation that I'll mention a little bit later. A third approach has been to consider that there is relativistic turbulence behind the shocks. So you have the relativistic bulk velocity, and then you say you have shocks, and you argue that behind the shocks then you have turbulence, which is itself relativistic. So you have bulk Lorentz factor gamma, which is maybe 300 or 500, and then relativistic eddies with a gamma turbulence of maybe 10 or 20. And those change direction, and so then they cause radiation, which gives you a very nice variability. The problem is that these relativistic turbulence is unlikely to remain turbulent, relativistic for a long time. As soon as the eddies, if the eddies are relativistic, as soon as they collide with each other, they will thermalize. They will become non-relativistic. And in fact, numerical calculations confirm that. So this was an interesting model, but I don't think it works. Another model is Zhang and Yang, where it's called the ICMART model, internal collision, magnetic. But the idea is that you have magnetic fields in the shells being ejected, okay, and initially the magnetic field lines are all parallel, so you cannot have reconnection. But the initial collisions, they can distort the magnetic field lines, and then you can have field lines of opposite polarity, and those can then reconnect. And you get magnetic, you have a combination. It's something like internal shocks, but with magnetic reconnection. And that seems to give pretty good radiative efficiency. Okay, let me get down to some more detail about the hadronic internal shocks. So as I mentioned, they are more efficient, okay, and so they would be occurring in the internal shock. And in the initial version of hadronic models, one considered that the gamma rays are produced by some leptonic mechanism, electrons accelerated in the internal shock, and then the protons are accelerated, but it was only interesting for doing neutrinos. But more recently, so we've considered what happens with the secondaries from these P-gamma interactions, not just for doing neutrinos, but for making leptons secondaries, which are then re-accelerated, and then they can produce, you can produce synchrotron radiation and inverse phantom and secondary synchrotron radiation. So you can calculate the photon effect, the electromagnetic radiation from these hadronic secondaries. And so you can do that, let's say you can assume a radius for the dissipation region, either a photosphere and internal shock, and then inject electrons and protons, which are first order Fermi accelerated, typical spectrum. You allow them to cool subject to synchrotron, inverse phantom, pair formation, photomeson, everything. And then you consider the reacceleration of the secondary leptons, maybe by scattering of turbulence or just shock reacceleration. And then you can get with some plausible assumptions, you can get a self-consistent photon spectrum, an MEV band photon spectrum, plus a second GeV hard component as you get in lab. And you get something which has a good radiative efficiency, which doesn't violate the IceCube neutrino limits, but you're not able to make up to GZK energy protons. So you accelerate protons, but they don't quite get up to these type of calculation up to GZK energies. So this is an example of the type of photon spectra you would get. Low energy spectra that are decent, high energy spectra photons that are decent, and then you get a second component. these would be the original secondaries, but then you have gamma-gamma annihilation that gives you this cutoff here. So there's a calculation by Glass as well. Another case for a different type of luminosity. So, you know, you get various spectra that look pretty decent. And finally, one thing that I didn't mention is that the high energy gamma rays, typically they will lead to pair formation, especially if you get backscattering of a few gamma rays from the external medium. That sometimes can get a pair cascade, and those pairs also increase the radiative efficiency. So there are various papers that explore that. All right, let me move on to discussing some of the connections of gamma ray bursts to cosmology. So as I mentioned, the gamma ray bursts are distributed isotopically. The spatial distribution is to high accuracy isotropic, and the log n versus flux is more or less a -3½ slope, as you expect in Euclidean geometry, and at low fluxes, meaning very high redshift, you get a departure. Essentially, it's the fact that the redshift of the sources makes them fainter. Okay, so it looks like a cosmological distribution, as it should be. These more details I showed you yesterday. And one of the other things that I didn't mention last time is that when you look at the GeV light curves, and I told you that the GeV photons come delayed with respect to the low energy MEV photons, both in long bursts and in short bursts. So there was a delayed onset of the GeV radiation. These has largely an astrophysical origin that you can explain with the geometry of where the GeV radiation is produced and where the low energy energy photons are produced. But it also has an application towards putting some limits on quantum gravity. An interesting type of result. So regardless of any additional astrophysical effects, if you just consider what you can say about quantum gravity. So you know that quantum gravity as a theory doesn't exist so far, but there are effective low energy theories of quantum gravity which consist of essentially making a low energy series expansion of the full theory. And if you do that, then you find that what these effective theory indicates is that there will be an energy-dependent dispersion of both boson and fermion signals. Namely that either bosons or fermions, either neutrinos or photons or whatever, will travel at an effective speed. It's as if they had a refractive index, that they will travel at different phase velocities. And so what you have is that you have wave dispersion, and so you can expand the effective so the Lorentz, these would be the normal Lorentz invariance condition, but now you have additional terms in a series expansion. If you're considering photon signals, E photon over the quantum gravity energy scale to the first power, plus E photon to the quantum gravity energy to the second power, plus higher order terms. And so that means that you can have the photons of different energies traveling at an effective different velocity. And so that would imply that there is a time delay between high energy photons and low energy photons, which depends on the quantum gravity energy scale for n power, where this is n to the 1, n to the 2, and 3, etc. And then these are just the normal cosmological terms. So these are an effect that you expect from quantum gravity, in addition to any astrophysical effects. Okay? And so you figure that if you put some limit on delta t, then you'll have a limit on m quantum gravity. And so you can do that, and you find that for specific examples, for the n equals 1 term, you can say that the quantum gravity energy scale has to be greater than about 1/10 of the Planck energy. So at that time, and that was a conservative lower limit, so at that time that was the strongest limit yet on the observational limit or experimental limit on the Planck energy scale, the quantum gravity energy scale. Then a little bit later, a burst a year later, or 6 or 7 months later, a short burst, one got an even stronger limit that the n equals 1 term, the quantum gravity energy scale has to be greater than a few times 10 to the 19th. That means that one can rule out the n equals 1 term because it exceeded the Planck scale. The Planck scale is 1 point something, 10 to the 19th, and it was several times 10 to the 19th. So you could say that any such series expansion, that term is 0. At best, the next term is non-zero. The limit on that is, of course, not good at all, but we could say that in such a series, this term doesn't exist. So this is actually a significant result, and it's so far the best results on type of effective theory expansion. All right. So now, where do the GRBs fit in terms of their distance? You probably have GRBs. You certainly have GRBs up to redshift 9.4. That's the highest limit. And probably we have them to 15 or 20 or so. Probably where the first stars form, wherever that first population 3 stars form, 20 or 30. Gamma ray bursts must start occurring because you form massive stars which will collapse to a central black hole. Some of them will be rotating fast and will have GRBs. Beyond that, you have the so-called dark ages, then you have the CME. And these regions here, so up to about 6 or 7, that region you can study pretty decently with AGNs, Fouriers, etc. But 7 to 20 or so, really we don't know much at all. And so that's a region where GRBs can be used for studying the sort of, youngish universe, but not at some depth where the universe was maybe 1/10 or 1/20 of its present age. Now, how would those GRBs look like? So in the optical, of course, there is the intergalactic hydrogen, Lyman alpha, introduces a cutoff in the spectrum. And so the optical spectrum would look like, for redshift 1, you get a cutoff here, 10 to the 15.2 hertz, and redshift 3, you get the cutoff here, and for redshift 5, you get the cutoff here. And these are various photometric bands, U, V, R, I, etc. And here you get into the range of infrared, which is where JWST has detected the operate. If you look at, so that's as far as how the spectrum looks like. As far as the flux, so it turns out that there is a positive K correction of the luminosity. So as you go to, so the spectrum is a parabol, and as you go to higher redshifts, you're observing the lower frequencies, and the lower frequencies, the flux is higher. So you find that actually the flux that you get at high redshift doesn't diminish, especially, doesn't diminish very much as you consider higher and higher fluxes. So for the same luminosity burst at the redshift 5, its flux at 2 microns is not much different at 1 hour at the redshift 14 or 15 than it was at redshift 5. This is an effect of this positive correction. So they seem like an attractive type of object to use for studying high redshift objects. The detectability, either with X-ray detectors, Chandra or Swift, is pretty good. So here's the Chandra limit, and up to is what a typical burst would look like at high redshift. So you can detect them up to fairly several hours. By Chandra goes deeper than Swift, so you can detect the X-ray emission up to redshifts of 20 or so. The problem is that we may be seeing an X-ray, signal, but we don't have a signature for telling us where it is. So just because we see an X-ray time-varying signal, there is no guarantee that it's a GRB, and there is no guarantee that it's nearby or that it's far. The same thing is true if you consider the James Webb Space Telescope, Future Telescope, K-band or L-band. You have good detectability up to redshifts of 15 to 20. Now, high redshift bursts have been observed photometrically. For instance, this is the Lyman cutoff, and that Lyman cutoff was instrumental in giving these z equal 6.29 redshift. Photometrically, it was argued that it was a high redshift. Then Subaru obtained the spectroscopic redshift, which confirmed high value. In fact, it gave a much more accurate value. Before, photometrically, one just said it was higher than 0.6, but he put the exact photometry. And the thing here is that at high, GRBs also in X-rays are extremely luminous. So if you consider, for instance, these GRB here, redshift 6.29, the same I pointed out before, this is X-ray flux as a function of time. Okay? It's for one whole day, this X-ray luminosity is brighter than the brightest X-ray AGN that the Sloan Digital Survey has found. So for up to 10 to the 5 seconds, that is for one day, the X-ray luminosity of these bursts is larger. And up here, it's about 10 to the 5 times larger than the brightest X-ray AGN. So it's a huge luminosity. And so you can use it as a sort of flashlight illuminating through the intergalactic medium. And it's a continuum spectrum. So it's like an X-ray synchrotron spectrum that you can use to shoot through material to, to find what are the absorption lines of the intervening material. What is the chemical composition of the intergalactic medium between that object and you? One of the interesting things with the high redshift bursts, including the highest ones, is that they appear to have in their own restraint, they appear to be short duration. Yet they're so luminous that we think they must be core collapse objects, not binary neutron star mergers. So there is discussion as to whether they're really long bursts and we only see the tip of the light curve because it's in the noise, or whether they're truly intrinsically short for some other reason. Maybe the collapse is much faster, or maybe they're binary neutron star mergers, but in that case they should be much more energetic than the usual ones. So these objects are observed. They're very luminous, but there is some difficulty in understanding how you would sort of understand them in terms of massive star collapse, which is what they should. All right. So I mentioned that these objects have so far the largest redshift. It's a photometric redshift, but it's quite believable. The EISO is not crazy, it's 10 to the 53 Earths, it's similar to some of the other ones. Because it's so far away, its E peak is relatively low. And it was detected by a variety of detectors, and then eventually Gemini, so for a couple of days robotic telescopes looked at it and estimated the redshift. Eventually Gemini was put into action, and that got these supplementary redshift by the Lyman alpha cutoff. So with 99% confidence level, it's high redshift, and these sort of 95% confidence level. Now, the distribution of bursts in redshift, as far as the observed ones, looks more or less like these. They peak around redshift 2 or so, 2 or 3, and they taper off as you go to higher redshift. So if they're connected to star formation, then more or less these should correspond to, have some connection to the star formation rate. Here is the same plot in terms of the look-back time. So compared to the star formation rate, which is this gray affair, these are the data here. So there is some correlation between the star formation rate and the GRB density at high redshifts. It's not perfect, so there could be a bias factor. And so in fact, is the star formation rate, is the GRB, observed GRB distribution. They fit better here than they fit here. It seems that the GRBs, if you plot the metallicity of the host, so there is the metallicity, quantity of metals of higher Z elements than hydrogen, compared to the solar metallicity as a function of redshift, and you find that the GRBs tend to appear in higher average metallicity host galaxies than the average galaxies. So these are the metallicity of the average galaxies, and these the metallicity of the GRB host galaxies. So they appear to arise in relatively metal-rich, more metal-rich, at the same redshift of the more metal-rich host galaxies. Now I mentioned phenomenological correlations. I mentioned two of them in particular, the Amati relation and the Lambda relation. There have been several others. One of them was the variability time scale versus E gamma ISO. The other was the lag between different energy bands and gamma ISO. And then there were more complicated correlations between three variables: EP, EISO, and T-break, or EP, EISO, and T0.45, which is a vibration measure, where these actually is also correlated to the variability numbers. The best established ones are these So anyway, these are the correlations look like, if you remember. And so the idea is that if you have measured EP from these correlations, you could infer what is the ISO. And that might help you to convert your to a standard category, which you might use in cosmology. So basically, you measure EP and you measure an observed flux, and your observed flux differs from you get an observed flux, you compare it to the EISO that you reduce from the EP, and that gives you a redshift. So that makes them into a standard candidate that you can use for cosmology. And so what you can do is do a Hubble diagram. And this has been done with supernova. Okay, you plot the distance modulus, the apparent magnitude versus the absolute magnitude as a function of section.